Okay, applications of integration, page 6. Continue with kinematics. Since the velocity is equal to the derivative of the distance can be found by taking the indefinite integral of v of t. The integration constant is the initial position. The definite integral of v of t between t1 and t2 would find the displacement, actually the change in position or displacement between t1 and t2. Okay, here's a complex procedure to find total distance traveled if there are direction changes. So first you draw a sign diagram for v of t so that we can determine any changes of direction. Remember, a sign diagram looks like this, and what you do is you find any stationary points of velocity. When does the velocity equal 0? At what times? And then, like, in between, it's going to be the positive or negative. Okay? Afterwards, you determine s of t by integration, including a constant of integration. So, you use the sign diagram to find these stationary points here and here. And when you do the integral, you're going to have part of the integral, it's above the x-axis, part of it's below. So whenever you take the, whenever you want to find the distance traveled, you can't let the negative parts cancel out with the positive parts, because otherwise it might end up being 0, and you know that you didn't walk 0. You walked to the left, you walked to the right, but in the end you walked quite a long distance. So you have to count each area as an area which adds to the other area. So if it's a negative area, you have to multiply it by -1 so that it counts. Then you find the displacement at t1 and t2. So you're finding the displacement at each time that the direction changes. And then you draw a motion diagram. Remember, motion diagrams, they look kind of like this. And then determine the total distance traveled from the motion diagram. Because the motion diagram, it's going to change direction every time it gets to one of these critical points. Every time it gets to one of these critical points, it's going to change direction. And then if you add up like all the lengths here, then that's going to give you the total distance traveled. So under what circumstance can we simply use the integral with the modulus below? So when we use technology, or with the TI-84. Okay, so when you use the calculator, you can just tell the calculator, hey, I want to do absolute value, and the calculator will automatically do that. Draw arrows to show how you go from one quantity to another by differentiation or integration. Okay, so remember that to go from displacement to velocity, you take the derivative. And when you go from velocity to acceleration, you also take the derivative. When you go from acceleration to velocity, then you're going to do the integral. And then when you go from velocity to displacement, you're going to find the integral also. Okay. So 19C2. A particle has a velocity function v equals 1 minus 2t as it moves in a straight line. The particle is initially 2 centimeters to the right of O. Write a formula for the displacement function. Now, remember, to get the displacement function from the velocity function, we integrate. So we're going to take the integral of this velocity function, 1 minus 2t, to find the displacement function. Let's see. And we know that it initially starts 2 centimeters to the right of O. So the reason why that helps us is that's going to be the integration constant. So when we take the integral of 1 minus 2t, we're going to get t minus 2t squared divided by 2. Hey, look at that. The 2's cancel out. So we actually get t minus t squared. And we're going to integrate, we already have the integration constant. So t minus t squared plus the initial position, which we know is 2. So we can just, instead of S0, we can put 2. Okay. So that is the formula for the displacement function. That is part A. Find the total distance traveled in the first second of motion. So, if we put t equals 0, that's going to give us the initial position, which is displacement equals 2, right? If we put t equals 1, that's going to be, let's see, 1 minus 1 plus 2, it's also 2. Wow, look at that. So it actually starts at 2, and after 1 second, it is still at 2. It must have moved somehow. So in between t equals 0 and t equals 1, there must have been a direction change. So let's go back to the procedure to find the total distance traveled when you have direction changes. So the first thing we're going to do is draw a sign diagram for v of t. So v of t is 1 minus 2t, right? And so when is, if we're going to draw a sign diagram for v of t, then we find the critical points first. So 1 minus 2t, where are the critical points? We set it equal to 0. We discovered that the critical point is at t equals 1/2. Hey, what do you know? That's exactly between 0 and 1. So there is a direction change at 1/2. That's the 0 point. And to the right, if we put a bigger number than 1/2, then we are going to get a negative velocity. And if we put a smaller number than 1/2, then we are going to get a positive velocity. So that is our sign diagram for velocity. And what's the next step here? The next step is to determine S of t by integration, include, okay, we already did that. And then we're going to find the displacement at t1 and t0, which would be 0 and 2, and we already did that too. We discovered that it's actually at the same position in both cases. It's at position 2 at the beginning and at the end. Okay. And then we need to find S of t at the direction change. The direction change, remember, is at t equals 1/2. So at t equals 1/2, the displacement would be 1/2 minus 1/2 squared, which is 1/4, plus 2, which is 1/4 plus 2, which would be 8/4 plus 1, which is 9/4. Okay, so that is the displacement at t equals 1/2. Then we draw a motion diagram. Okay, so the motion diagram says that we start at s equals 2, and then we are going to go first a positive velocity, so we're going to move to the right, and then we go until we get to position 9/4, which is also 2.25. At 2.25 and at t equals 1/2, the motion diagram changes direction, and it goes actually exactly back to 2. And the timestamps for these, I'm going to draw it in a different color so I don't confuse you. So it starts out t equals 0, of course. At t equals 1/2, it's changing direction 2.25. And then at exactly t equals 1, it reaches back to the original position 2. So the total the displacement at the end of 1 second is this, which is 0.25, and this, which is negative 0.25, but we're going to add both. And then so actually, you know, the displacement, the total distance traveled is going to be 0.5, right? So the answer to B is 0.5 because we added 0.25 together twice. And then find the displacement of the particle at the end of 1 second. It's going to be s equals 2. I guess technically it's s equals 2. But, you know, it started out as like s equals 2. So really it hasn't displaced at all. Okay? So that's it for page 6. Right? Yeah.